Good morning, students. Myself, Vijay Shankar from EC Department, Chapel Engineering College. Today, we are going to discuss about another topic in the magnetostatics, that is the fourth unit, force between differential current elements. Force between differential current elements. See, the electrostatics, we studied that a point charge exerted a force on another point charge. Means in electrostatics, if there is any charge is there in the space plus q. If there is any another charge, let us take q1 is charged in the free space, and q2 charge is placed nearer by to the q1. This force is exerted due to the q1, the F2, 1, 2, due to the q1, charge q1, a force is exerted on the q2. Okay. While the discussion in the electric fields, we studied that a point charge exerts a force on another point charge separated by a distance r. The distance is r. Separated by a distance r, the force is exerted, and here also the force is exerted is from due to the 2r. When already there is a q2 charge is there, we replace the q1 with the distance of r. The force is exerted on the q1 due to the q2. Okay, either it is either you can bring the q2 or the q1. There is a force is exerted separated by the distance r. If these charges are of same type, both positive or the negative, then they are repelled to each other. Repel. Opposite directions. Plus is a repel to each other. Minus is also repel to each other. If it is a plus and minus means attractive. But when the two charges are different type, one positive and other negative, they are attract to each other. Same charges means repel to each other, and opposite charges, one is positive and other one is a negative, means they are attracted to each other. This is in the electrostatics. Now, in the magnetostatics, it is not on the charges, it is due to the current. Now, consider a two current carrying conductors. Consider a two current carrying conductors are placed parallel to each other. Parallel to each other. Is one conductor. Current is I1, current is passes through this conductor in upward direction. And another conductor, I2 current is passed through the second conductor. So both the currents are in the same direction. Then the force is attracted. Same direction means same direction. There is an attraction occurs for the two conductors. Consider the two current carrying conductors are placed parallel to each other. Each of these conductor produces its own magnetic flux around it, because a conductor carrying current surrounding there is a magnetic field. Surrounding there is a magnetic field. According to the Fleming's right hand thumb rule, the thumb is in the upward direction, means the magnetic flux or the magnetic field is in the anti-clockwise direction. And the downward means clockwise direction. Got it, my dear friends? Each of these conductor produces its own flux around it. So when such two conductors are placed close to each other, there exists a force due to the interaction or inter-reaction of two fluxes. The force between such parallel current carrying conductors depends on the directions of the two currents. The force is either it is attraction or it is a repulsion, depends upon the current flows. Depends on the direction of the two currents. Okay. If the direction of both the currents are same, listen my dear friends, if the direction of both the currents are same, then the conductors experiences a force of attraction in the figure A. If the directions of both the currents, if the directions of both the currents is the same, then the conductors experience a force of attraction. Force of attraction, the two conductors. And in the figure B showing that the current in the conductors is opposite direction. I1 is in the upward direction and I2 is in the downward direction. The force is in the opposite, repel to each other. Force of attraction, force of repulsion. Okay. And if the direction of the two conductors are opposite to each other, then the conductors experience a force of repulsion. Okay. The direction of currents are same, there is a force of attraction. The currents are opposite to each other, the force of repulsion. Got it, my dear students? Now let us consider the two current elements. The two current elements, IDL1 bar and IDL2 bar. Is a line current, IDL1 bar, and here IDL2. Always it is a positive to the negative flows. Here also the positive to the negative flows. Okay. So positive here, I1 is flowing in this direction, upward direction only. And similarly, I2 is also in the same direction. A small differential length assume on the in the IDL1 bar, and in the second conductor, that is I2DL2 bar. And the distance between of these two is R21. Okay, from here we are taking R21. From here you can take that is R12. From 1 to 2, that is R12. From 2 to 1, that is R21. The direction is the same. The distance is the same. Either you can start from the 1 to 2 or 2 to 1, both are the same. Let us now consider the two current elements I1 DL1 bar and I2 DL2 bar as shown in the figure. Note that the directions of I1 and I2 are the same. See here, I1 and I2 are the same. Got it, my dear students? Both the current elements produce their own magnetic fields because the conductor carrying current surrounding there is a magnetic field. As the currents are flowing in the same direction through the elements, the force D of differential of F1 bar exerted on the element is I1 DL1 bar due to the magnetic field of D or differential magnetic flux dB2 bar. And due to this, there is a force is exerted. Okay. And due to this, there is a force is exerted on the second. Because the same direction means the force is the attraction. When we'll get this force, if there is no any second conductor, there is no any force will exist here. When the second conductor is there, due to the second conductor, the force is exerted. If there is no any first conductor, only the second conductor is there, there is no any force. Okay. When the first conductor is there, then the force is exerted due to the first conductor. See here saying that is a DF1 exerted on the element I1 DL1 bar due to the magnetic field of second, due to the magnetic field of the second conductor, the dB2 bar. Produced by the element I2 DL2 bar is the force of attraction. If suppose this force is D of D F2 bar means F2 bar exerted on the element I2 DL2 bar due to the magnetic field of dB1 bar. Understood, my dear students? D of DF1 bar is the current IDL1 bar. The force will get due to the magnetic field of dB2. Got it? And here the dB1. Then from the equation, the force of from the equation of force, the force exerted on the differential current element is given by the D of D. the differential F is equal to IDL bar cross B bar. So F bar is equal to IDL bar cross B bar. Okay, F bar is equal to, there is a line integral, F bar is equal to K bar cross B bar into ds. Another F bar for the volume is there, J bar cross B bar into dV. In the last class, we derived this expression. F bar is equal to IDL bar cross B bar, or it is a F is equal to IDL B sine theta. Got it, my students? So IDL bar cross B bar, we are now applying the differentiation here. dF1 bar, the dF1 bar is the dF2 bar, dB2 bar. The d of dF1 bar is equal to IDL1 bar cross dB2 bar. According to the Biot-Savart's law, the magnetic field produced by the current I2dL2 bar is given by the free space B2 is equal to the differential current, or the B2 is equal to mu naught into H2. B2 bar, or it is also H2 bar. Now, if I am taking the differential, dB2 bar is equal to mu naught into dH2 bar. What is the dH2 bar? According to the Biot-Savart's law, mu naught is equal to, not the mu naught is equal to, mu naught into I2dL2 bar cross AR21 by 4 pi R square. That is R is R1212 bar. Okay, this is starting itself. We derive this expression. Got it, my students? Now the dB2 bar you can substitute in the differential of the differential F1 bar is equal to mu naught into dB2 bar IDL1 bar cross. You see this? What is the expression here? The d of dF1 bar is equal to I1dL1 bar cross dB2 bar. Okay, IDL1 bar cross the total function. I1 dL1 bar cross I2 dL2 bar cross A2 bar AR21 bar by 4 pi R square into mu naught. Already the mu naught is there. So now there is a two differential elements here. The d of means two integrals. One is for the dL1 bar and other one is a dL2 bar with respect to the L1 and with respect to the L2. The remaining is a constant. Mu naught I1 I2 by the 4 pi. The integral L1 and integral L2 dL1 bar cross dL2 bar cross AR2 by R square. That is from 2 to 1. Okay. And similarly, I told that the differential current, the D of dF2 bar is equal to D of dF2 bar is equal to I. Previously we have that is I1. Now it is I2 dL2 bar. I2 dL2 bar cross B differential current dB1 bar. Got it, my students? Differential of differential F2 bar is equal to I2 dL2 bar cross dB1 bar. So what is that B1 bar? According to this, B1 is equal to mu naught into H1. So I2 dL2 bar cross, according to the Biot-Savart's law, using this B1 bar is equal to mu naught into H1 bar. What is that H1 bar? Mu naught into, previously we wrote that is I2 dl2 bar. Now it is I1 dl1 bar. Cross A. It is from 2 to 1. Now AR 1 2 bar. Whole divided by the 4 pi R square 1 2. Got it, my dear student? Now you can substitute these in the differential element of dB bar. D of dB bar is equal to dH bar. What is that value? IDL2 bar cross mu naught into I1 DL1 bar cross AR 1 2 bar whole divided by the 4 pi R 1 2 square. Got it, my dear students? That is equal to, you write the mu naught in the outside, and I1 and I2 is also the outside. I1 and I2 outside, whole divided by the 4 pi is also, you can write the outside. And we have the line integral of 2, line integral of 1, DL2 bar, cross, here the DL1 bar, cross A R12 bar by the R12 square. Two equations we got. That is the F1 bar is equal to and F2 bar is equal to. See, it is the mu naught I1 I2 by 4 pi and mu naught I1 I2 by I2 I1 by 4 pi. Both are the same. And here the cross product is DL1 bar cross DL2 bar cross AR21. Either it is a 21 or 12. Both the distance is the same. Okay, but the direction is a difference. Whenever if it is a R12, AR12 is this in the direction, but this unit vector A21 direction is a difference. The force is F1 here and the force is F2. F1 is equal to minus F. Distance is the same, but the direction is a difference. So F2 is equal to minus F. F2 is equal to minus F1 or F1 is equal to minus F. Thus, the above condition indicates that both the forces F1 bar and F2 bar obeys Newton's third law, that for every action there is an equal and opposite reaction. For the two current carrying conductors, the length L each, the force exerted is given by F is equal to mu I1 I2 by 4 pi into the distance is there. The distance is, we can write as L by D. The total force L by D, the mu I2 I1 by the, actually it is a 4 pi, the 2L by D. The distance is the D, the same. And DL bar cross IDL bar cross here 2 bar will get the 2L and 2 to get cancelled, here the 2 1. Where I1 and 2 are the currents flowing through the conductor 1 and the 2. And the D is the distance separated between the two conductors. Distance is the same. From either it is a 1 to 2 or 2 to 1. The distance is the same. If the two current flows in the same direction, the current carrying conductors attract each other. While if the two currents flow in opposite direction to each other, the current carrying conductors are repelled to each other. Opposite direction is a repel and same direction is a attraction. So find the force. The force either you can take from 2 to the 1 and the 2 to the 2. The force is mu into I1 and I2 L by 2 pi into D. Got it, my dear students? The next topic is a magnetic dipole. We see in the electric dipole is a P bar cross AR bar or PD. Now the magnetic dipole, that is T bar is equal to M bar cross P bar. It is a P bar cross AR bar. Now it is the magnetic dipole, the torque can be expressed as T bar is equal to M bar cross P bar. Your M bar is a IS into N bar and T bar is equal to B into IS. Okay, the cross product you can take it as a T bar is equal to M bar cross P bar, the magnetic dipole. So the difference between, now here there is a difference between of electric and the magnetic circuits. Electric and the magnetic circuits. You see for the electric circuit, in the electric circuit the current actually flows. That is, there is a movement of electrons. Movement of electrons. In the magnetic circuit, due to the magnetomotive force, flux gets established and does not flow in the sense in which the current flows. And second point, the difference between the electric and the magnetic circuits, the energy must be supplied to the electric circuit to maintain the flow of current. And here the magnetic, the energy is required to create the magnetic flux, but it is not required to maintain it. And the third one is the resistance and the conductivity are independent of current density under constant temperature. And here the reactance and permeability are all the different dependent on the flux density. And fourth point, the electric lines of flux are not closed. They start from the positive charge and end on the negative charge. The magnetic flux are closed lines. Okay. These are the difference for the electric and the magnetic field. That is not much important, my dear students. Now go for the another topic. In the electrostatics, we discuss about the capacitance. Now in the magnetostatics, we discuss about the inductance. When the coil with N turns carrying current, the flux is produced by it. This flux linkage with each turn of coil, thus the total flux linkage of the coil having N turns, N5 Weber turns. Okay, the flux linked with the coil is proportional to the current flowing through it. The ratio of total flux linkage to the current produce that flux is called the inductance. What is the inductance here? The ratio of total flux linkage. The ratio of total flux linkage to the current producing that flux is called inductance, and it is denoted by the L measured in a Henry. That L is equal to the total flux linkage to the total current. What is the total flux linkage? L is equal to, this is for the solenoid, my students. For the solenoid, total flux linkage by the total current will get the L is equal to, total current is I, and total flux we got the mu into N square I by A into L. I get cancelled. L is equal to mu N square, where N is the number of turns. A is the area of the solenoid. The solenoid means it looks like this. It's a solenoid with the length of L. And now the inductance of this solenoid, the length of the solenoid is a L, and total flux linkage depends upon the number of turns and area of the solenoid. Mu into H bar, actually it is a mu, B is there. B is nothing but the mu into H, or it is a B bar is equal to mu naught into H bar, or the mu into H bar. L is equal to mu N square I A by the L, where A is the area of the solenoid and L is the length of the solenoid. The total flux linkage is a mu N square I A by the L, and total current is I. So L is equal to mu into N square A by the L is the inductance of the solenoid. The same thing, the inductance of the toroid. You can take the toroid, inductance of the toroid. Consider a toroid ring with the N turns. Toroid means it looks like this, my dear students. I already told this is a toroid. Okay. Its circumference is a 2 pi r. Magnetic flux density inside the toroid ring P is equal to mu Ni by the 2 pi r. Mu Ni by the 2 pi r. Consider a toroid ring with N turns and carrying current I. Let the radius of toroid is R, capital R. The radius of the toroid is a capital R. Then the magnetic flux density inside the toroid ring. Magnetic flux density inside the toroid ring is P is equal to mu into Ni by the 2 pi r. Where Ni by the 2 pi r is a H, because the B is equal to mu into H on. Got it, my students? So L is equal to, we got L is equal to mu N square H by the 2 pi ln of R2 by the R1. R2 by the R1 is a inductance of the toroid ring. L is equal to mu N square H by the 2 pi ln of R2 by the R1. Next is the inductance of the coaxial cable. Inductance of the coaxial cable. Consider a coaxial cable, inner conductor with a radius A, outer conductor radius is a B, and the Gaussian surface is there, and this coaxial cable distance is the D on the Z axis. You have to find out the coaxial cable inductance L is equal to also. So I will briefly explain these inductance of the coaxial, inductance of the solenoid, inductance of the toroid. All it will get from the total flux linkage inductance L is equal to total flux linkage by the total current. L is equal. Okay. By using the solenoid, by using the toroid, or by using the coaxial cable, inductance of, not the by using, my dear students, inductance of the solenoid, inductance of the toroid, and inductance of the coaxial, not using here. The inductance of the solenoid L is equal to inductance of the toroid L is equal to inductance of the coaxial cable. First, I am saying that it is an inductance of the solenoid. Inductance of the solenoid. See here the inductance of the solenoid, the first one. What we got, the inductance of the solenoid is given by the L is equal to total flux linkage by the total current. Total flux linkage by the total current. Actually, what is the total flux linkage means? L is equal to N-phi by the I. N-phi by the I, where L is the inductance in terms of, not in terms of the L is equal. Total flux means N-phi by the total current I is equal. So the length of the solenoid is L, and is the current passing through that solenoid here. I already draw this as solenoid like this. The current is passes in the direction with the length of L. L is equal to. Consider a solenoid N, a solenoid of N turns. This is as shown here. Let the current flowing through the solenoid I is an amperes and the length of the conductor and cross-sectional area E. Okay. The field intensity inside the solenoid is given by the H is equal to the field intensity with the magnetic field intensity. H is equal to Ni by the L, where the current is passes to this solenoid and N is the number of turns in the solenoid and L is the length of the solenoid. The H is equal to amperes per meter current in terms of the amperes and L is the meters, where N is the number of turns. H is equal to Ni by the L. Got it, my dear student? The total flux linkage, whenever it is L is equal to the total flux linkage means N into phi. N into phi by I actually. What is the N into phi? The N into the phi is equal to integral B bar dot ds bar. B bar dot ds bar. If I use it as a magnitude only, B into ds. Okay, B into ds. Where the B into integral of ds means is a surface area only. Okay, totally the integral of ds we can take as a S as A. So B into A, the phi is equal to, you can write it as a B into A. So the N phi by I, the total flux linkage, N into phi is a B into A, whole divided by the current I. Got it, my dear friends? So N into, what is the B in terms of H? H is equal to mu naught. B is equal to, or not the mu naught, mu into H. Me into H value. Now I'm substituting that is a B as mu naught into H A by I. That is equal to N into mu naught. What is the H here? Ni by L. The magnetic field in the solenoid is the length of the solenoid and the current is passing, current which is passed, and N is the number of turns. H is equal to Ni by L into A is already there. N into mu naught H A, H is Ni by I, Ni by L into A, whole divided by I is a total flux linkage. N into N square, that is a N into N is a N square, mu naught, I and I get cancelled here, N square into mu naught A by L, where L is equal to the inductance of the solenoid. L is equal to mu, not the mu naught, actually it is a mu only, my students. You can write the mu N square A by the L. Okay, inductance measured in the head. Got it? The second I told inductance of the toroid. Inductance of toroid, my students. The toroid having the ring is with the radius of R. Toroid ring with the radius of R. And the current is passes through this having the number of turns like this. The toroid ring with the radius of capital R. Okay. Consider a toroid ring with n turns carrying current I. Let the radius of the toroid is a capital R. The magnetic flux density or the H is equal to, first of all, you can see the magnetic flux, magnetic field. Magnetic field is previously in the solenoid Ni by the number of turns and the passage of current through the number of turns by L. L is the length of the solenoid. Now, if I am taking it as a toroid, means H is equal to Ni by 2 pi r. Okay, the 2 pi r, the area of cross section of the toroid ring is a 2 pi r, where A is R is the radius of the ring. Got it, my dear students? Now the B is equal to, what is the B is equal to? Mu into H. That is equal to mu Ni by the 2 pi r. If it is a length, we can take it as the length of the solenoid L. Now it is a toroid ring with the radius of R. A is the area of cross section. When we consider as a phi is equal to the magnetic flux is equal to B into A. And that is L is equal to the total flux N phi by I. That is equal to N into phi is B into A phi I. So what is a B here? The mu Ni by the 2 pi r we got. Substitute here. N into B is a mu Ni by 2 pi r as a B into A by not the A, by I. So I get cancelled, and N into N, it becomes of N square mu A by 2 pi r is the inductance of the toroid ring. L is equal to N square mu A by the 2 pi r, where A is the cross section of the toroid ring, that is a pi r square. Also you can write this. For the toroid ring with n number of turns, H has a height of the toroid with R1 is the inner radius. With R1 is the inner radius. See here, this R1 is the inner radius, and R2 is the outer radius. R1 is the inner radius, and we can take it as R2 is outer radius. Then the inductance is given by. So actually, the inductance of the toroid with if I am taking only the radius of R, N square mu A by the 2 pi r. If we take number of turns, n number of turns, H has a height of the toroid. L is becomes the inductance L is becomes mu N square is already we get here also. L is equal to N square mu A by the 2 pi r. Now it is a mu N square. H is the height of the toroid, and R1 and R2, it's a 2 pi. I'm not taking with this radius of R. Ln of inner radius is R1 and outer radius is R2. Outer radius by the inner radius. So L is equal to mu N square H by the 2 pi ln of R2 by R. Otherwise, L is equal to N square mu A by the 2 pi r. Both are the same idea. If you given the inner radius and outer radius to find the inductance of the toroid means, we can use this formula. L is equal to mu N square H by 2 pi into ln of R2 by R. If they given only the area and the capital R, the radius means, can use to find out the inductance of the toroid is N square mu A by the 2 pi r. Got it, my dear students? We got the same inductance of here. The L is equal to mu N square H by the 2 pi ln of R2 by the R1. Got it, my students? And to find the inductance of a coaxial cable, this is a coaxial cable. Inside the radius is A and outside the radius is B, and the Gaussian surface is R, and the distance of a coaxial cable is a D. What is the inductance? What is the inductance? To find the inductance, L is equal to total flux N phi by I. That N phi is nothing but N into P A by I, where phi is equal to integral B bar dot ds bar as in the vector product, or the P into integral ds. Integral ds is a differential surface, means it having the area only, the P into A by I. For this coaxial cable, the field H is equal to whatever the current is that is passes I by, there is no any number of turns, my dear students here. If for the solenoid, it is a n number of turns and the current that is passes and the length of the toroid, or the length of the solenoid. And for the toroid, number of turns n and I is the current and its radius, the toroid ring radius is R by the 2 pi r. Okay, now the coaxial cable, H is equal to, there is a coaxial cable means there is no number of turns, n is equal to 1 here, I is I by, now here you can take as a 2 pi r. The 2 pi r with the radius is there here. Consider a coaxial cable with inner conductor radius A and outer conductor radius of B, inner conductor of radius A, outer conductor of radius of B. For the coaxial cable, the field intensity at any point between inner and outer conductors is given by, means inside you can consider as a Gaussian surface. We already know H is equal to I by 2 pi r. I by 2 pi r, we derive this expression into A phi bar. Whenever the Gaussian surface is in between of the A to B, I by 2 pi r into A phi bar. Okay. So H is equal to I by the 2 pi r, I by the 2 pi r, and the B that is equal to N into mu H by HA by I, mu HA by I. What is the H we got? N into mu, H is I by 2 pi r, I by 2 pi r into A, and already the I is there in the denominator, the total current, I get cancelled. N into mu A by, it's not the capital R, but it's a small r. The Gaussian surface here, it is a small r only. N mu A by the 2 pi r. Okay. Or if suppose it is in terms of the radius of B and the radius of A, whatever we derive, the height we consider, the inner radius is R1, outer radius is R2, ln of R2 by the R1. Now the coaxial cable, if the coaxial cable is there, mu I is equal to B is equal to, whenever if I am taking the B is equal to I by the 2 pi r, means B is equal to mu into H. That is equal to mu into I by 2 pi r. It is in the phi direction, the A phi bar. Here also the A phi bar is there. B is equal to the differential surface. The differential surface in along the phi direction. Differential surface along the phi direction as a dr dz into A phi bar. Got it, my students? So using the phi is equal to integral B bar dot ds bar, B bar dot ds bar is equal to, as of integral B mu I by the 2 pi r, A phi is there, and ds bar is equal to dr dz. Dr dz. dr means one integral r is equal to, r is varies from a to b. R is equal to a to b because the radius is inside is a and outside is a b. Another integral for the z. Z is a distance is a d on. So z is equal to 0 to d. Supply the dr is equal to. So phi is equal to, we got as mu I by 2 pi r with 1 by r is there. So ln of b by a, and with the dz with integral we'll get the d. So mu I d by 2 pi into ln of b by. Substitute that phi is equal to, where L is equal to n into phi is mu I by 2 pi ln of b by a into d whole divided by the I. So I get cancelled. L is equal to n into, here there is no any number of terms, my dear students. The total flux also don't take it is a n. The total flux is only the n phi is already there. So there is no any n. We have the mu d is there, d ln of b by a whole divided by the 2 pi. Whole divided by the 2 pi. L is equal to mu d ln of b by a, the 2 pi. So n is, there is any number of terms here, you can consider it as a 1. L is equal to mu d ln of b by the 2 pi. We got the inductance of solenoid, inductance of the toroid, inductance of the coaxial cable. Okay, my dear.